Hello, everybody. Welcome to our webinar on ClickHouse and OpenTelemetry, where we're going to both show how to store distributed traces in ClickHouse, and then we're going to use distributed tracing to trace ClickHouse itself and show some of the inner workings. I'm very excited for this webinar. Thanks again for joining us. And I'm Josh Lee. I'm the open source advocate here at Altinity. I know just enough to get myself in trouble, and that's why I am here supported by Maciej. Maciej, would you like to introduce yourself?
Hello, everyone. I'm Maciej, and I'm a support engineer at Altinity. Well, hello, everyone.
Thank you. All right, so quickly, our agenda. We have an hour today. A lot of it we're gonna save some time for. We have two demos for you today. One really short one in the middle, and then a longer one at the end, where we're gonna really dive into some of the stuff and some of the code behind it. Before we get to that, we're going to do a very brief version of what is distributed tracing, what is OpenTelemetry, and why ClickHouse is maybe a good choice for doing distributed tracing with OpenTelemetry. If you've already seen me talk, it might be a little bit repetitive. I'm going to go through it pretty quickly. If you haven't seen me talk and you're like, oh, wow, he went through that really, really quickly, then go ahead and find any of the YouTube videos where I've done it. This sort of 5-minute intro that I'm going to give has been done as like a 20-minute or 45-minute talk all over the country. Then we're going to talk about ClickHouse for observability and why ClickHouse makes a great data store for all of your telemetry signals, but especially traces and logs. We're going to show a short demo of sending OpenTelemetry traces to ClickHouse and visualizing them with Grafana. And then Maciej is going to talk to us about the architecture of ClickHouse, how we can, what tools are built into ClickHouse that we can use for observing ClickHouse itself. And then we're going to go into a longer demo where we show some distributed traces from an actual running ClickHouse cluster across the various nodes. And possibly, if we have time, even show some of our exciting new work with Project Antalya, which is all around connecting ClickHouse to the data lake for infinite scalability. All right, so with that, let's dive in. So the way I usually start is by making fun of logs, right? And this usually gets a laugh when I'm doing this talk live because logs are an easy punching bag, right? They're easy to make fun of. We all have been frustrated by having to read just way too many logs trying to find that needle in that haystack. But if you think about it, I think maybe we're too hard on logs, right? Because they're actually the fundamental building block of everything that we're doing with observability. So if we look at this, this is a basic request log that I'm sure we've all seen, many, many times. And typically this will be in structured format in your system, hopefully, but just for readability here, we have it in plain text. We have our timestamp, our duration, our HTTP verb, our endpoint, and our response code. And it turns out if we have all of those things for every request inside our system, and we can count those things, we can build a really awesome dashboard like this with all of our RED metrics, right? Request, errors, duration, or golden signals, as Google likes to call them. So we start to get really, really valuable metrics out of those request logs. And so with the combination of metrics and request logs, we can kind of answer the questions like, is something wrong? And then maybe, hopefully, if we can find the right log message, we know what went wrong. But that's a key point, right? Can we find the right log message? So how do we do that? And that's where I think distributed tracing can be really helpful. I see a question, will the recording of the video be shared? Yes, the recording will be shared. We will be following up with an email with the recording for everyone who signed up, as well as links to some of the code samples and some follow-up blog posts. So no worries if you have to drop. And also, if you do have any other questions, feel free to drop them in the chat or the Q&A panel at any time throughout. And if I see them, we'll try and stop and answer them. Right. So if we take those logs and we simply add a request ID as a first step, that's really useful because then we can tie each log message back to the end user action that it's responsible for. But that gives us just a bag of logs that we then have to correlate imperfectly using timestamps and things like that. So what tracing does is it actually just encodes all of that useful information of hierarchy and what called what in the log messages themselves. So we're really only adding two fields to our log. We're adding a span ID and a trace ID. And then for child spans, we will be, excuse me, adding the parent span ID. And that allows us to structure our logs in this tree structure. Right, so we have these new fields. And we get this amazing tree structure, this waterfall-like graph that tells us all about the latency of an individual request and also the exact order of what called what when. So if there is an error in one of these calls, we can reverse the path and see exactly what led to that error. So this is, excuse me. I think this graph is immediately apparent how valuable this is for things like understanding latency or understanding the cause of events leading up to an error message. But I think distributed tracing is also much more powerful when we think about them in aggregate, right? Because when we think about them in aggregate, then we start to understand entire pieces of our system, the architecture of our system and the topology of our system. But observability is not any one signal, right? We need them all. We need metrics, we need traces, we need logs. The fundamental characteristics of metrics is that they're aggregable. I would argue right now they're mostly pre-aggregated, but if we had good enough traces, we wouldn't need to, if we had a good enough storage engine that could compress those traces and store all of them in an unsampled nature cost effectively, we wouldn't necessarily need to pre-aggregate our metrics, and we could slice and dice them after the fact based on any new dimension that we might not have thought of, that we might not have built into our instruments that's actually embedded in our code and our binaries. So we have our metrics, they're aggregable, whether it's pre-aggregated or post-aggregated. We have our traces, which help us zero in on where the problem is. That's what we're going to be talking about the most of the day. And all of that is in service of finding that log message that has the error that you're going to go Google. And I've kind of mentioned all of these reasons why I think distributed tracing is the killer app for this workflow. It lets you understand the complete request flow, as we saw. By combining them and aggregating over them, we can create a real-time map of our system topology and all of the dependencies. We can derive metrics from that across any number of dimensions and with essentially unlimited cardinality, unlike with metrics where we have to be very, very careful and guard our cardinality. And finally, we can make our logs so much easier to find by attaching them directly to a trace message. We don't quite have that yet in this demo, but that is something that you can do with the OpenTelemetry specification, where you can have all of the relevant log messages attached to the relevant traces, making them so much easier to find. So that's where we come to OpenTelemetry. And I think that one of the reasons the OpenTelemetry project exists is because of the need for an open standard for distributed tracing. In fact, I think it's the main reason the OpenTelemetry project exists. If we think about logging and metrics, which have been the traditional way to do monitoring, the standards are essentially text, right? Logs are just text lines that you can feed into other systems. Maybe there's ways to denote metadata and key value pairs and things like that, excuse me, and tags. But at the end of the day, they're just text. And so interoperability means, does your thing speak text? Yes, my thing speaks text. And for metrics, it's mostly the same thing, right? Metrics are very simply a number and a bunch of tags that go with that number. And so you can kind of see how that is in itself just an open standard, right? Prometheus, the standard, how the metrics are exported by a Prometheus exporter, can be read by any number of things, not just a Prometheus agent. So it's already more or less an open standard. But with distributed tracing, we didn't have anything like that, and we actually needed a way to get the request IDs, those trace and span IDs, need to be propagated from the incoming request down into all outgoing requests. So we needed to have something that could hook into the actual internal state of our applications. We needed some kind of embedded SDK. And without OpenTelemetry, we were left to use SDKs from vendors and actually embed those SDKs in our artifacts. Yes, this will definitely be later on YouTube. So that's really why we needed OpenTelemetry, is because now we don't have to go and put vendor code in all of our code artifacts that are distributed out there. There might be tens of thousands at a large organization, right? Which means that all of our code artifacts can have a vendor-neutral open source instrumentation that's speaking of vendor-neutral open source language that we can then use with any tool or any number of tools at the same time. And that's really, really awesome. And that's why we have OpenTelemetry. So what actually is it? Well, I think the most important part of OpenTelemetry, the part that empowers all of this interoperability, is the specifications themselves. That's OTLP, which is the wire protocol for how telemetry signals are transmitted over the network. It's the semantic conventions. Naming things in software is really, really hard. Semantic conventions give us easy, consistent names to use so that we don't have one team using HTTP_requests and another team using requests camel case count. For the exact same metric, right? Those kinds of things can actually consume all of the time of a central SRE or observability team just because things aren't named consistently. And then we have the W3C trace context. This is the open specification for how trace ID and span ID get put into HTTP headers and propagated to downstream services. So if you put those three things together, really any tool that is compatible with those three things is OpenTelemetry compatible, even if it's not using any of the OpenTelemetry provided code from the OpenTelemetry community. But of course, the OpenTelemetry community does provide us code and implementation so that we can use these things right away, right? So we have the language-specific SDKs and APIs that I've been alluding to. Those are what get dropped into our programs themselves and let our programs emit tracing, especially, right? And there's the instrumentation libraries. So say we're using something like Express. The OpenTelemetry instrumentation library for Express knows how Express works and knows how to observe Express's HTTP calls and how to inject headers into the outgoing HTTP calls. And so you can get automatic instrumentation of Express just by adding a single Node.js library. And there are hundreds, if not thousands, of instrumentation libraries available for the various under-the-hood libraries that you might be using in any of the 11 languages that are supported by OpenTelemetry. Then there's the OpenTelemetry collector. This is something that we're using in our demo, and we'll show you some of the configuration for. It's very much a Swiss Army knife, but you can think of it as an alternative to a vendor agent. So it can both work as a node or a cluster agent, gathering node and cluster level metrics and logs. And it can also act as a proxy for telemetry from your applications, forwarding it to the backend of your choice. So in our demo later today, we actually have a couple of different OpenTelemetry collectors deployed. We'll talk about that. And then there's all the extensions, right? OpenTelemetry is compatible with, at this point, pretty much every monitoring standard that I'm aware of under the sun through the power of extensions. It's extremely extensible, and that's one way that you can get more and more data out of the OpenTelemetry collector and into any of the supported backends, such as ClickHouse. And of course, as I mentioned, it's vendor neutral, it's open source, and it is the second most active CNCF project, which is awesome. There are so many people contributing to this project and using this project. And it is actually one of the few instances in the entire world of software where we have format compaction. Open census and open tracing both existed. They merged, and now we have OpenTelemetry. So we have one fewer standard. I think that's beautiful. We now also have OpenTelemetry co-evolving with Prometheus so that we can have harmony between those standards. I think that's also beautiful. So here's the little picture putting kind of all the pieces together. If we were to build an entire pipeline using OpenTelemetry, right, we would have our service with all of those various components that go inside of our service, the API, the SDK, the library instrumentation, and our manual instrumentation. Then we have the collector with all of its extensions. It's got receivers, processors, and exporters. Those all pretty much do what they sound like. Connectors take the output from one pipeline and feed it into the input of another pipeline. So a really useful one is the span metrics connector, which can do that, some of that post aggregation that I was talking about. It's still doing it, on your nodes, not necessarily in your backend, but it's a little bit more immediately configurable to do your aggregation at the agent level rather than at the SDK level. And then, of course, we would have a backend where you're going to need something for dashboards, something for ad hoc queries, some kind of analysis UI that usually provides both of those things, right? It's going to be querying for data from your storage. And then you might also have a framework for alerts that's also going to be rapidly querying your storage to check for any patterns that match any of your alert settings. All right, so I mentioned storage there. And in our demo, what we're going to be using for storage, of course, this is why you came to this webinar, is ClickHouse. So very quickly, what is ClickHouse? For those not familiar, it is a SQL-compatible OLAP database. OLAP meaning it is great for analytics and things where we're interested in the aggregate of many rows, not so great at individual transactions like an OLTP database, Postgres being one of the more popular examples of that. It's columnar. This architecture is part of what makes it OLAP, right? Makes it very, very fast at reading all of the data from one column because you want to do math on all of the data from one column. Which is a very common thing that we're doing, right, when we're talking about observability use cases. It is really, really fast. Anytime an architectural decision, there's an architectural trade-off in ClickHouse between speed and something else, 9 times out of 10, the choice is we're going to go for more speed. So that just makes it really, really fast. There are tons of optimizations under the hood that ClickHouse is doing to just make it as fast as it can be for the types of workloads that we're going to be talking about. During our second demo, Maciej is going to dive into some of that architecture that makes all of that possible. It is petabyte scale, right? So we can go up to several petabytes, dozens of petabytes. For now, we're working on Project Antalya, which brings ClickHouse to Iceberg and Parquet formatted data lakes on S3 compatible object storage for theoretically infinite scalability. And ClickHouse eats cardinality for breakfast. Thank you to Last9 for giving me this way of expressing it. But yeah, you just really don't have to care about cardinality in ClickHouse. In a system like Prometheus, high cardinality might be dozens or hundreds, right? In a system like ClickHouse, high cardinality means millions. So it's just in a completely different ballpark when we're talking about cardinality compared to some of the other tools that we might be used to. And it's very, very optimized for write once, read many workloads, which is essentially what we're doing with observability, right? We're ingesting events at a very, very high rate, and we need to record them, and then we almost never need to update them, right? Once a trace is completed, it's complete. We can ship it to our database. We want to analyze it, maybe derive some metrics from it, but we never need to update that record. And at a certain point, we're going to want to delete it when we don't care about it anymore. So this write once, read many architecture of ClickHouse really lends itself to that type of workload. And how it works is we kind of have the data gets written into a partition. And in the background, ClickHouse is merging those partitions and optimizing the order in which everything is written so that it can be read as quickly as possible. So you get this ability to do these small writes that can be very, very fast. And in the background, the data is merged so that you get more and more efficient reads as your data gets more and more compacted into larger and larger ordered partitions. So this is really, really cool. It gives us a bunch of benefits for observability workloads. It's time friendly, right? If we're ordering that data by the time on the timestamp on the telemetry signal, that's usually the way that we're going to be reading the data. So we're reading the data aligned with the way that it's written to the actual disk, which makes everything very, very fast. We have easy cleanup because everything is written and partitioned by time. When something is past our retention policy, we can just delete an entire partition, and there goes all of our telemetry that was more than 2 weeks or 3 months or whatever our retention policy is. We get TTL, right? Automatic time to live. So we can just automate that process of deleting the old partitions or moving them to cheaper storage if you want to archive them, maybe for compliance reasons. And that would be an interesting use case for Project Antalya, where you could actually TTL your data and keep years worth of telemetry data without needing to sample it because it's on super cheap it's compressed and then stored in super cheap object storage. As I mentioned before, right, of course, you have extreme cardinality. We have excellent compression within ClickHouse, even in semi-structured data like JSON blobs and mapped columns, and you get flexible schema, right? So you can use things like JSON and map columns. So let's talk about using ClickHouse for observability. There's a bunch of integrations that make ClickHouse really great for observability. Two that I'm going to show in my demo later is the OpenTelemetry collector exporter. This is an extension for the OpenTelemetry collector that can export traces, metrics, and logs to ClickHouse. It uses SQL. And that is essentially what that means is that any of the 90 plus things that can be received by the OpenTelemetry collector can now be exported to ClickHouse in one of those 3 signal formats, which is awesome. And then for actually visualizing and working with that data, we have a Grafana data source plugin. There are actually 2, one maintained by us at Altinity and one maintained by Grafana. They both have, there are reasons to use both of them. Then you might have something like the Kafka connector, right? This is maybe not a common use case, but something that I see at very, very large scale organizations where you might have all of your telemetry already in a single Kafka pipeline, and then you just want to use a sync connector to dump that data into ClickHouse and do analytics with it. So that's something that you can do with ClickHouse if you're at that scale. If you're at a much smaller scale and you want something that's just drop in, ready to go out of the box, CoRoot, Signals, and ClickStack are all fully open source and more or less complete observability platforms that include an agent, a backend, an analysis UI. Signals has alerting. I believe CoRoot and ClickStack have some rudimentary alerting, and all 3 of them use ClickHouse under the hood. So if you're like, wow, Josh, everything that you're talking about today looks really, really awesome, but I don't want to build it all myself, those are the 3 things that you're going to want to check out. Quesma is a really cool tool that essentially provides an ELK-compatible API on top of ClickHouse. So if you're already using some kind of Elastic or OpenSearch compatible tool and you would like the performance of ClickHouse, Quesma can provide a translation layer for you. And then, as I've mentioned, right, we're working on Project Antalya, which will integrate ClickHouse with Iceberg and Parquet for all of the cheap and scalability, the cheapness and the scalability that come with that. I don't want to spend too much time on this because I want to make sure that we save time for our demo, but the OpenTelemetry collector, right? I kind of already mentioned how we're using the exporter to send the data to ClickHouse. Really common receivers that you might use would be like the OTLP receiver, which would be a great way to receive traces from the OpenTelemetry SDKs. You might use the host metrics receiver to get to use the collector as like a node agent. You can use the file log receiver. That's also part of my demo from the webinar that I did last fall. That gathers all logs from, in that demo, a Kubernetes cluster, but you could also use it for a host that's not on Kubernetes, right? So we have a ton of receivers. Commonly, you're going to be using the batch processor. In my demo, I'm using the K8s attribute processor, which just adds metadata for the Kubernetes pods and things where the telemetry is coming from. And it tries to do that dynamically and intelligently, so I don't have to think about it too much. And then, of course, right, we're using the ClickHouse exporter. If you wanted to use something like Jaeger, you can actually use ClickHouse as the underlying storage engine for Jaeger. So commonly, I will use Jaeger to test telemetry in a development environment, and I'll actually use the memory storage engine. I won't have a persistent storage engine. But you can also use ClickHouse, and this might be great if you are using Jaeger in production and you really want the scalability benefits of ClickHouse. You can't use the all-in-one Jaeger Helm chart. You have to split out the various components. So what you do is you end up deploying an OpenTelemetry collector, or really anything that's capable of exporting Zipkin traces. So that might be a Jaeger agent. And then that's going to export via OTLP or Zipkin to the Jaeger collector component, which is one of the components of Jaeger that you can deploy. That has an extension, Jaeger ClickHouse, that uses gRPC to write the data directly into ClickHouse. And then Jaeger UI is using SQL to pull the data out of ClickHouse. I don't have a demo of this, but the net result, if you do set all of this up, is you get Jaeger trace spans that look just like any others, right? You're just using ClickHouse as the storage engine. Very little about the experience of using Jaeger will change. And I think it's a great way to visualize these individual traces, and it does give you a basic system architecture graph, but it doesn't have a lot of built-in capability for like aggregating information across all of your traces, or even necessarily for finding interesting traces if you didn't already know the specific trace ID or the attributes that you were interested in looking at. Another example of a visualization tool that has great capabilities for looking at individual traces, and a little bit more if you build it, right? If you build the dashboards, a little bit more capability to kind of discover interesting traces with things like heat maps and line charts and bar charts, right? Is Grafana. So this is what I'm going to actually use in my demo. We have an Otel collector using the ClickHouse exporter, speaking to ClickHouse, and then Grafana using the data source plugin to pull that data in. And actually, in this demo, there are two instances of the OpenTelemetry collector. We have one instance deployed as a daemon set to every node, and that is gathering cluster logs from that node. And then there's another collector set deployed as a deployment. I actually only have it scaled to 1, so I don't have it replicated for high availability like is implied in this graph, but you can imagine how simple of a change that would be, right? So I have this collector deployment, and it's responsible for receiving all of the OTLP data coming from the daemon set collectors and acting as a sort of a gateway so that there aren't too many connections going to the ClickHouse cluster. Another thing that the Otel ClickHouse exporter does is it automatically creates the schema. By default, you can turn it off, right? But by default, it automatically creates the schema in ClickHouse for you. So for me, it was nice to be able to control that and just have one deployment responsible for creating the schema. And then I could have multiple daemon sets, right? Say I have multiple clusters with different types of configuration required, sort of all pointed to that central deployment gateway. Then for ClickHouse itself, of course, I'm using the Altinity operator. This is fully free and open source and Apache 2.0, just like ClickHouse itself. It is by far the easiest way to run ClickHouse on Kubernetes. there's a Helm chart. So you just Helm install the Altinity operator. And then there's another Helm chart for creating the actual ClickHouse cluster, or it's a pretty simple custom resource. If you just want to create it yourself, it's a couple dozen lines of YAML, and you will get yourself a ClickHouse cluster. The Altinity operator can also manage ClickHouse Keeper for you. Keeper is responsible for maintaining consistent state across your ClickHouse cluster and coordination. So if you're doing high availability, you'll definitely want Keeper with replication and your ClickHouse cluster with some degree of replication. And as you scale, also sharding. All right, so let's quickly look at a demo showing how we're going to get traces into ClickHouse with OpenTelemetry. So for this demo, I have deployed just a couple of simple services, right? So we have Grafana, the OpenTelemetry collector, and then the OpenTelemetry collector again as a deployment. So this is a pretty simple umbrella Helm chart, just 3 subservices. And if we look at the values, right? So the first OpenTelemetry collector, this is configured. Well, it's not actually using this exporter, but it has the OTLP, the ClickHouse exporter. It's configured with the OTLP exporter pointing to our deployment instance of the collector. And it's got all of these presets turned on for gathering stuff from Kubernetes nodes, which is great. Gives us a bunch of logs. That's all from my demo last September. If you want to go check that out, it is on YouTube. Then we have this new instance, the OpenTelemetry collector deployment. This has some of that Kubernetes stuff turned off. We will enable Kubernetes attributes just in case we get any telemetry signals that aren't coming from one of those other collectors with the K8s attributes processors turned on. We have our ClickHouse exporter configured with our endpoint, database name, super secure username and password. That's always important, right? You always want to make sure that that's not just in plain text in your values like it is here. We're going to create the schema. We can give it the names for the logs. These are the defaults, but I'm just being super explicit here. And then, retry settings. All of these, again, are mostly the defaults, and I'm just being super explicit. And then we are also exposing an OTLP receiver. So this will receive OTLP on any port. Looks like our indentation got screwed up a little bit here. I'll have to check that before I apply again. And then we have Grafana pretty much set up, by default, as default with the security turned off. Because again, this is a super secure demo. And what we get from that is, so I've set up a very basic dashboard, right? This is not the state of the art of what you could do with Grafana and this data, but just to kind of show you that the data's there and give you some ideas for what you could do with it, right? So I'm using this library code Otel, and I just piped a few artificial traces into this ClickHouse instance so that we would have something to look at. In the second demo later, Maciej is going to have much more interesting traces for you. But we can see, right, I can create a graph for traces over time. If we edit this, we can actually see the query that's happening. Here, I'm using the upstream, the Grafana maintained plugin, because it has built-in support for OpenTelemetry. So you can just sort of check this box and say, yes, I'm using the ClickHouse OpenTelemetry exporter, and it already knows what all of the columns are. It knows how to map the schema to what Grafana is expecting for its traces. So that's basically the main work that we have when we're trying to visualize these traces in Grafana, is just getting the schema to match what Grafana expects for traces. And here we've done it using the plugin, the combination of the plugin and the collector exporter. In the later demo, we're doing it using a ClickHouse view, which is another way that you can very quickly alter the schema to match what Grafana needs. And then we have this list of traces. So one of the interesting things here, right, is that we have this service name, this operation name, and if we look at one of the actual individual traces, we can see the spans, of course. We also get these attributes, right? Resource attributes like k8s.pod.ip and service name, and span attributes that should actually be copied into the resource attributes. Yeah, there we go. So span attributes, things like the service.instance, service.namespace, right? These are the things that actually define the entities that you care about. So say you wanted to navigate your telemetry based on services, or the team that owns a service, or the services that are downstream from another service, right? All of those types of queries begin with this metadata right here. And that's one of the ways where ClickHouse not just being efficient at this, the storage, but also being a relational database that lets us connect the information together in a graph and then navigate that graph. This becomes really, really powerful, and we can do really interesting things with all of this metadata and create entities from it, and then use those entities as a way to navigate our telemetry as an alternative to time. So I think that's really cool. And was there anything else I wanted to show here? Thank you for the compliments on my new setup. Yes, that's also a public GitHub repo. So now, right, this is not a complete observability solution quite yet, right? As we were showing in Grafana, that was a very, very basic dashboard. Really what I'm showing here is sort of the collection, sampling, and processing and the storage blocks from this diagram that I show often as sort of what are the components of a more or less complete observability solution. So we're not doing a lot on the analysis and UI side. I haven't set up any alerts, so of course I could do that using Grafana Alert Manager. We're using OpenTelemetry for the application SDKs and the host and node agents in this case. But if you wanted something that you could just drop in and work out of the box, I mentioned it already, CoRoot is a great choice. Signos is another great choice, right? And ClickStack is another good choice. And just to look at this CoRoot screenshot really quick, this is combining OpenTelemetry with another awesome distributed tracing tool called eBPF. eBPF is not just for distributed tracing, it's part of the Linux kernel. It's used for a ton of things, but since it allows us to observe other processes from inside the Linux kernel, it's really, really powerful for observability and especially distributed tracing. And so this screenshot comes from just using eBPF without any OpenTelemetry at all. CoRoot also does speak OpenTelemetry, and there are other tools that would speak that would use eBPF agents and export that data as OpenTelemetry so that you could use it with any OpenTelemetry-compatible backend. And again, that's one of these really cool things about OpenTelemetry is that it is so interoperable as long as you're speaking the specification. You don't have to be using the built-in implementations. So that's enough about that. That brings us to ClickHouse architecture. Maciej is going to take over for me here and walk us through how ClickHouse is actually doing all this awesome stuff.
Hello, everyone. Once again, thanks, Josh. So for those who don't know ClickHouse, it is super easy to start with. You just do apt-get install, you have SQL, it reads most of the format, it compresses data superb, and it's really fast. So how does ClickHouse actually process and insert? Can we get another slide? Thank you. So in this example, most people does not insert data this way. ClickHouse offers a variety of methods for data insertions, from integration with messaging system like Kafka to reading data from external sources like S3. It can even connect to MySQL, Postgres, and it reads most of the formats like JSON, Parquet, and so on. So what is exactly happening inside ClickHouse? In short, like in any other database, query is going to arrive into the database. ClickHouse will do some parsing, analyzing, and planning. Data will be sorted, indexes will be built, and then insert will be executed, creating what we call parts, which are immutable segments of the table, and those will be flashed to disk. The key thing to know here is that the data will live in memory while insert is being processed. So if we go to another slide, that insert into format was pretty simple query. So what we want to do is to parallelize the process in order to execute it faster. ClickHouse has a setting, max insert thread, which tells ClickHouse on how many threads to use when performing the insert. This particular setting applies only to the insert into select. And for the plain insert, like insert into from the CSV or TSV, those are also parallelized by input format parallel parsing, which is also enabled by default. For this example, we use 4 insert threads. So select will read the source table in the parallel by max threads. setting by default is all available CPUs in the system. Every thread will allocate memory to read and pack the columns in blocks, and those blocks will be squashed to bigger ones, and then parts will be created. And if table has partitioning, each partition will need to have separate parts, which later will be built in memory and flashed to disk. So in the course of the operation, ClickHouse can create many parts by each of the thread, and each thread needs to have space in memory in order to perform the operation. For insert into selects, it's basically two separate parts, insert and the select, and both of them needs a memory. So you cannot create like too many parts because later you have that merging process, which can take I/O and resources. So it's important to create as bigger part as you can. So this is how the data insertion look into ClickHouse. If we move to next slide. Now we will talk about how ClickHouse processes query with aggregates. So this is quite interesting. If you have a group by, like here in the example, we calculate the average delay for a carrier for flights table. And after the ClickHouse will parse the query, it will build the memory structure, it will analyze the query, apply some optimization, and then planner will tell the executor how to get the data. So as I mentioned, ClickHouse by default will use all available CPUs to execute the query. So each thread will do the scan over the data, over the parts, and it will run it down using streaming functions, which will read the data in groups. We called it buckets. And those buckets will have a hash tables that eventually will be merged. And at the end, it will be passed back to the user. So here there is no caching layer built into the reading data. ClickHouse rely on the Linux page cache to make things faster. So if you do I/O over the same block, it will read from memory if it's available. It's efficient and transparent caching layer. So how the query is parallelized? So as I said, each thread will split data into the buckets, and it will calculate the partial aggregates, which later will be calculated to final aggregates. Those are accumulated, those partial aggregates in hash tables, and internally it's called a state, aggregate state. For example, for the count aggregation, the partial aggregation state is simple and incremental update count variable. And for average, that partial aggregates calculate the weighted average. So it remembers the values, the numerator, the denominator numbers. And in the end, it merges it to the final aggregation. So it looks just like MapReduce, like in other databases. So every aggregates in ClickHouse follow this process. It has just different representation of the data that is partially aggregated from. Actually, ClickHouse aggregation is more sophisticated than this. For example, the aggregation is dynamic. So like those hash tables can be split in multiple levels to allow merge hash values in parallel. This is basically what's going on, and this is all happening in the memory. You can enable spill integration to disk and sorting, but it will slow down the query. So better don't use it. Okay, so maybe now I will show you the distributed tracing inside ClickHouse. I will share screen. Just a second.
I think
Josh,
I need to release it somehow. I'm trying to. Yep. Okay. There we go.
okay. So as you can see here, this is Grafana, and we are using the trace component here. Visualization traces. And I executed the simple group by query over the ClickHouse cluster with 2 replicas and 2 shards. And as you can see here on the trace details, we can see all the traces from inside the ClickHouse. It's built in. It saves the traces into the OpenTelemetry span logs table. And what's important here is that by default, those built-in traces cannot trace distributed queries. So this needs to be done manually for now. But as far as I know, ClickHouse team is working on this. So as we can see here, query is being executed. We have all the information that we need. So it was executed on the first of the node. If we scroll down here, we can see that another node executed it. And since it's distributed table, that ClickHouse will delegate some part of the queries onto the another nodes. So if you have 2 replicas, that default load balancing is random. So we will choose one of the node, execute the group by query. It will do the partial aggregates, and then it will aggregate it once again on the node that query was executed. So we can see here that query was sent to the ClickHouse tree, and some aggregation was done. This is what we can get from the OpenTelemetry built in the ClickHouse. And what's most interesting, we can even do that for the Antalya project. For those who don't know, Antalya extend the ClickHouse storage onto the Iceberg. So we can have really cheap storage on the Iceberg with fast executing queries. What's most important here is that we have what we call swarm clusters that are scalable pools of self-registering stateless ClickHouse servers. So ClickHouse node, which runs the query, we call it vector, delegates the read, for example, for the packet files to the swarm, and those swarm node executes the query. So as we can see here, it's simple query that reads from the Bitcoin transaction on the public blockchain on S3, and I'm delegating the reads to the swarm cluster. So as we can see here, we have 4 swarm nodes, and each of those nodes has done some work. So we can scroll here. You can see here that second node executes on the object. it has done some aggregation and so on. And you can see the same on the others. So here's the first one, the third one, and so on. So here it's the trace details, and yeah, it can be easily used to track your queries if it executed slow and so on. Okay, so I think that from my side, this is all.
Yeah, it's so cool. So just for everybody, right? I want to really make sure we're clarifying. These trace spans are coming directly out of ClickHouse itself. It stores all of these trace spans for its own operations. So with other databases where you might get a span, like an exit span for the service that called the database, and then you would just sort of be like, oh, there's a database call there, and it took 8 seconds, and you're not going to have any other insights into what happened inside that database call. Here, what we're seeing is like the actual communication between ClickHouse nodes, and we would also see communication like with Keeper in these traces, right? So you can see everything that's happening behind that curtain of the database call with distributed tracing that is built into ClickHouse, that is OpenTelemetry compatible. Like all of that is just so cool to me. I love it, and I wish that more tools worked this way, and I think that they can in the future, right? We just have to pay attention to these things, use open standards, and build observability in from the beginning. I think it's great. Do you mind if I take over the screen quickly, Maciej, and we'll just do some final thoughts, and then I'll throw up some links and QR codes for folks while we take questions. There was one question already, which was how do we make sure not to create too many small parts? And the answer that I put in chat, but I'll just read it out loud for everybody, is you can use the OpenTelemetry batch processor in the Otel collector to make larger batches. There are some settings on the collector exporter for ClickHouse, and then we have a knowledge base article that Maciej shared that we'll also make sure to include in that email to everybody about atomic inserts. Right, so final thoughts. I mean, I've kind of said this, right? Like all of this stuff is just awesome. Distributed tracing is awesome, especially for understanding applications. For us, ClickHouse is an application. For you, it might not be. It's just part of your infrastructure. But for us, ClickHouse is an application, and distributed tracing is awesome for understanding your applications. You might want to consider ClickHouse as a massively scalable telemetry data store if you are doing DIY observability at your organization. And if you're not doing completely DIY observability, then you might want to consider some ClickHouse-based observability tools like the ones that we shared, especially if you're dealing, if things like cardinality and dimensionality are important to you, you don't really want to think about that stuff in advance. You want your database to just handle it so that you can figure it out later. And tools with built-in observability, that's just awesome. Let's see more of that. I love it. Way to go, ClickHouse team. And yeah, so this is a QR code for a blog post where we compare some of these tools. I'm going to be doing more in-depth deep dives on these this summer, so make sure you stay tuned for that. We're going to be talking a lot about these tools and observability with ClickHouse, and trying out ClickStack and Signals and CoRoot and getting into the differences and the pros and cons of each. You can come talk to us on Slack. It's a great place to ask questions if we didn't get to any of your questions today. And that GitHub repo doesn't actually exist yet, but it will by the time that we send out the email later today, and it'll have all of the examples that we showed you. And now I open the floor to questions. On that Otel collector, yes, if you do use the batch processor, it will require more memory to make the larger batches. Okay, and then there's one more question. Thank you. You're welcome, Sanjeev. Our pleasure. Oh, maybe there's some questions in chat. Okay, Maciej, as you're answering questions, let's read them out loud. First one is question QA might require more memory in the app to make larger batches. Oh, yes, we also answered that in the Q&A. How do you handle traces with an app with 20,000 requests per second? Can I just only enable traces for errors? Yes. So the OpenTelemetry collector has a bunch of tools built in for sampling. So, and that's, you can also sample at the source. You can sample at the source, which is just going to be the most efficient, but then you're doing what's called head sampling. You don't actually know if there was an error in the trace yet when you're emitting it. Or you can do sampling in the collector using a strategy called tail sampling, where you wait until the trace is completed to see if there was an error, and then you make a decision about whether or not to sample that trace or not. So all of those are options in the collector. It does come with challenges in that you need to make sure that you're recording the ratios at which you're discarding spans, so that you can recreate any dashboards or counts that might be derived from those spans. But certainly, if you're dealing with 20,000 requests per second, that might be something to look into. Although that being said, ClickHouse certainly could handle trace spans at that volume if you scale it correctly. Yeah, and that's how much I answered also. Okay. Okay. Andrew Wang says, we were concerned about cardinality, but from your talk, it seems ClickHouse can handle it. Can you explain a little bit more about how it is able to do it? And if we do hit ClickHouse cardinality issues and need to split, any suggestions on how or what fields to do it on? Timestamps. Maciej, do you have any insights there in terms of like how ClickHouse handles such extreme cardinality? And have we had customers who've actually had to split up a column because of cardinality issues?
So what needs to be said here is that ClickHouse indexes are sparse. That means it's not like a B-tree index. It just saves min and max values for each granule. So if you have like high cardinality column, you will have to just save min and max onto the index. So basically, we do not recommend high cardinality columns in the order by class. But if you need to have them, yeah, then you just need to be aware that the index will be stored in memory in ClickHouse.
Yeah. So not keeping it in the order by it might mean like, say you have a dimension in that is high cardinality and you do want to use it in an order by, maybe correct me if I'm wrong here because I'm the beginner, but you might like make a materialized view with a subset of the dimensions, and that can do some of the pre-calculation for you so that the queries are faster.
No, I mean, if it's not string column, then it's fine to have it in the order by.
Okay. That might be something I follow up on with the blog post, because I am also curious about all that, Andrew. Henning Schmick asks, if he sends metrics over the collector and sends them to ClickHouse as is, no changes or processing, is the default schema good, or is this more like a first shot? The default schema is pretty good. I've heard from some people that they're using it in production just fine. I have also heard some people had some scale issues with the way that they were reading the data, and so they made minor adjustments to the schema just to suit their read case a little bit better. But unless you're sort of hitting extreme scale, then the out of the box schema should be good enough. And if you do want to refine it, go ahead and ping us in Slack, and we would love to help. We have experts. Okay. Any more questions? Is there a ClickHouse schema that matches semantic conventions? The semantic conventions mostly have to do with what goes in that resource attributes and span attributes column, which is a map. So the schema is very flexible, and you can also invent your own attributes that you might want to throw in there. I would prefix those with like an app.key or something, just put some prefix in there that's specific to you, so you know that you added them. But yeah, it's a very flexible schema. And then this is actually one of the cases where some minor changes to the default schema can help. All of these might have been contributed upstream already. but just ordering that map schema so that the keys are always written in the same order has a dramatic impact on performance and compression. You don't have to always have the same keys, they just have to always be in the same order. Thank you. Our pleasure. All right, so this recording will go out later today, and we got another question. Okay, will there be a native config to export Otel traces instead of a URL table? That's something we're thinking about, right? I'm thinking that might take the form of an Otel receiver that can kind of pull the traces out. That would be one way to do it. But yeah, this is something that we still need to explore more, is better ways to get those traces out of ClickHouse. All right, thanks for coming, everyone. And if you're in the New York City area, come join me later tonight. We're hosting an event. Details are on our website. Thanks again for coming, and see you next time.
Everyone, bye.